Hey everybody, it's Miss Berry. In today's video, I'm going to be covering section 1.1, which is about thinking mathematically. I'm going to go ahead and switch over the camera, and we're going to look at our whiteboard. All right, so here we have our notes, section 1.1, thinking mathematically. This section is all about reasoning. Reasoning is defined as the drawing of inferences or conclusions through the use of statements offered as explanation or justification. So we're going to be drawing conclusions using statements that are offered as explanation. There's two different types of reasoning that we'll be talking about. Inductive reasoning and deductive reasoning. We're going to talk more in depth about inductive reasoning first. It says inductive reasoning is a line of reasoning that arrives at a general conclusion based on the observation of specific examples. So it's going from specific examples to a general conclusion. We're going to see that deductive reasoning does the opposite. All right, so inductive reasoning goes from the specific, it gives you specific examples, and it's going to arrive at a general conclusion. And inductive reasoning can be considered a generalization. One example that I really like that I've used in the past, let me see if I can make my pen a little bit thinner. All right, so one example that I really like is Jose sneezed when he saw Mara's cat. Jose sneezed when he saw Josh's cat. Therefore, Jose is allergic to cats. So it's saying that it's giving you some specific examples. He sneezed when he saw Mara's cat. He sneezed when he saw Josh's cat. Therefore, he must be allergic to cats. Now, we'll talk more about this in a little bit, but generalizations may not always be true. So just because it is a valid line of reasoning does not mean that it's necessarily true. Okay, so we'll revisit that in a little bit. I wanted to show you some additional examples of inductive reasoning. We'll talk about why they are inductive. Remember, inductive is going from specific examples to a general conclusion. All right, so number one, my grade on the first test in quantitative reasoning was an 85, so I will make a B in the class. All right, so you made an 85 on the first test, so you're generalizing and saying, okay, so therefore I'm probably going to make a B in the class. This is definitely inductive reasoning. It starts with a specific example. So this is specific. And then it's making a generalization. So it's starting with a specific example and leading to a generalization. And then let's look at our second example. All known planets travel about the sun in elliptical orbits. Therefore, all planets travel around the sun in elliptical orbits. This again is definitely inductive reasoning. So you want to take a second and think about, okay, when I read this, what makes me realize that it's inductive reasoning? Okay, so it says that it's giving specific examples about all of our known planets, right? So all of our known planets travel about the sun in elliptical orbits. So this is specific to the known planets. So nothing about the planets that we don't know about. Therefore, all planets, that's a generalization. Okay, so that word all kind of gives you a clue that that's a generalization. I know it does say all here, but it's referring to all known planets, so it's kind of specific. All known planets travel about the sun in elliptical orbit. So it's this is generalizing, I guess, for the planets that we know. So it is still specific to the known planets. So therefore, all planets, generalizing to all planets, just by using something that we know about the known planets, all planets must travel about the sun in elliptical orbit. So that's what tells us that it's inductive reasoning. It's taking some specific examples, things that we know are true, and then it's generalizing it to all planets. Now, I wanted to talk more about the fact that inductive reasoning does not always result in a true statement. So, although this line of reasoning we were just looking at above, all known planets travel about the sun in elliptical orbits, therefore all planets travel about the sun in elliptical orbits. That is a valid line of inductive reasoning. However, that does not make it true. So, a counterexample is how you could disprove. So this is how you could disprove a line of inductive reasoning. All right, so it's just anything or let's say it this way, we'll say any one example of this statement, or we'll say the statement, not being true, will completely disprove the inductive argument. So sometimes lines of reasoning when you're will be called arguments. So if you can come up with even one counterexample, then it completely disproves the inductive argument. Okay. Oops. All right, so I wanted to go through some examples here. You're going to have a couple of these on the homework. Don't let them stress you out. If you can't figure one out, all you have to do is just take a screenshot of it, or take a picture of it and send it to me, and I can help you figure it out. It says, identify a pattern in each of the following sequences of numbers. Then use the established pattern to find the next term in the sequence. All right, so let's look at this first one. Let me zoom in a little bit. There we go. All right. 4, 9, 14, 19. Okay, so 4 to 9. So added 5. 9 to 14, added 5 again. 14 to 19, added 5 again. Okay, so we're adding 5 every time. So we should just add 5 to get to our next term in the sequence. So 19 plus 5 would be 24. All right, so there's our next term in the sequence, 24. All right, let's look at this one. 2 to 6. Okay, if you added 4, that would get you to 6. Let's see, so maybe we're adding 4. All right, what about here? 6 to 18. Oh, that's like adding 12. So yeah, that it's definitely not adding 4, right? So let's erase that. All right, what's another way you could get from 2 to 6? You could multiply by 3, right? Times 3. Let's see if that gets us to the next one. 6 times 3 is 18. Okay, so that works. 18 times 3 is 54. All right, so now that tells us what our pattern is. We're multiplying 3 each time. So 54 times 3 That'd be 12. So that's 162. Okay, and our last one, 5, 6, 8, 11. Okay. So in the last two, we've been doing the same thing every time. So maybe that's what we're doing here. Here we're adding 1. Okay, if we add 1, that would get us to 7. If we added 2, that would get us to 8. All right, and if we added 3, that would get us to 11. So what should we do to get to the next term? We should add 4, right? So 11 plus 4 would be 15. So that's the next term in the sequence. Okay, so since we're talking about sequences, this example illustrates our two different common types of sequences. The first one is called an arithmetic sequence, and then the second one is called a geometric sequence. So the arithmetic sequence, that was the first two examples. The geometric sequence was the last one. So I'm going to scroll down and just show you the definition of these two sequences. All right, so here we go. This is definitely something you want to write down. I think some of the questions on the homework ask stuff like, identify if this is an arithmetic sequence or a geometric sequence. So you may want to pause the video and write this down. So just to help you with how you pronounce this, it's arithmetic sequence. All right, so it says arithmetic sequences, the definition says, when the common difference between any two consecutive terms in a number sequence is the same, we call this an arithmetic sequence. All right, so let's go back and look at which ones were arithmetic sequences. All right, so on the first one, oh my goodness. All right, here we go. We were adding 5 each time, so you're doing the same thing each time. So that's an example of an arithmetic sequence. Here we were multiplying by 3 each time, so that's arithmetic. That's an arithmetic sequence. You're doing the same thing every time. Now let's go look at the definition of a geometric sequence. All right, so a geometric sequence says when the common ratio between any two consecutive terms in a number sequence is the same, we call this a geometric sequence. All right, so what that means, you may have to go back and pause that so you can write down that definition. But what that means is that you see how each time we were adding, we were going up by the same amount. So we added 1, then we added 2, then we added 3. So that ratio would be the same. Then that means that it's a geometric sequence. All right, so maybe that's a question that you could see on the test. It would just say like, identify the next term in the sequence. And then part B says, was this sequence arithmetic sequence or a geometric sequence? Okay. And then our last thing that we're going to talk about is deductive reasoning. All right, so we talked about inductive reasoning. We said the inductive reasoning is where you take specific examples and you draw general conclusions about those from those examples. Deductive reasoning is where you begin with commonly accepted facts and then you logically arrive at a specific conclusion. So you're going to start with some general facts and then you're going to arrive at a specific conclusion. All right, so that's deductive reasoning. You're deducting information about this accepted fact to arrive at a specific conclusion. Okay. All right, so let's think of an example of some lines of deductive reasoning. All right, so again, you're starting with something that's general. And then you're using those commonly accepted facts to draw a general conclusion. Okay, so let's say that maybe our general fact is all kids like cartoons. Okay, so that's a general fact. And then I could use this information to arrive at a specific conclusion like, therefore, I should include a cartoon on the cereal box I'm designing. All right, so maybe you are a graphic designer and you are designing a cereal box, marketing campaign or something like that. Since all kids like cartoons, I can use that general commonly accepted fact to draw a specific conclusion about the cereal box that I'm designing. All right, so here's some more examples. It says, identify whether each statement is an example of inductive or deductive reasoning. So remember, inductive is specific to general. Deductive is general to specific. All right, so if you live in New York, you are a resident of the United States. All right, so starting with a general fact, you live in New York. And then it's telling you something specific about the person. If you live in New York, you must be a resident of the United States. So again, we're going from general to specific, so that would be deductive reasoning. And then I have one more example I wanted to show you. This is off of the homework. It looks something similar to this. I actually took this one out of the textbook, but you have a little bar chart like this in your homework. It says Jessica has decided to start doing push-ups as part of her exercise routine. She is keeping track of the number of push-ups done each day using the given bar chart. All right, so here's her chart. On day 1, let's see. Let me get my pen. On day 1, she did 3. So day 1, she did 3. On day 2, she did 5. Okay, on day 3, she did 7. And then on day 4, she did 9. All right, so it says, how many push-ups will Jessica do on day 15? All right, so if you want to, we'll just list this out. So I'm going to go ahead and count down to day 15. Running out of room, I have to scoot my page down. Okay, so we're going up by 2 each time, right? So adding 2. Okay. All right, so we'll continue adding 2. So on day 5, 11, add 2, that'd be 13, 15, 17, 19, and then 21, 23, 25, 27, 29, and then 31. So on day 31, on day 15, Jessica would do 31 push-ups. Now, if you were asking like day 100, you may need to come up with a little formula. But since this was only day 15, it was pretty easy for us to just count down that way. All right, so that is the end of section 1.1, which is about thinking mathematically. If you have any questions about this section, please let me know. Otherwise, I will see you guys soon.